Hello everyone. So we are back to our plasma class. What we'll be studying today is non-thermal plasma sources. So in previous classes we have learned extensively about the arc plasma devices, and later we have introduced the radio frequency plasma devices, how they operates, and their the typical temperature profile, operating conditions, and typical structure. We have shown how the radio frequency plasma is generated over there. So in arc and these RF plasma devices, which are operating usually at atmospheric pressure or very close to atmospheric pressure, there the plasma generated is mostly thermal plasma. There may be little bit of non-equilibrium near the edges, but the core region is mostly thermalized. That is, electron temperature is same as the ion temperature or the gas temperature, but they are different from the radiation temperature. So now we will switch from the thermal plasma sources to non-thermal plasma sources. So I will explain you the basic principles of operation of this non-thermal plasma sources. The first one that I will explain you is called APPJ, that is atmospheric pressure plasma jet. And one such plasma jet you are seeing in operation on the upper right corner. So what you are basically seeing here, that explains a lot about the kind of difference and the drastic differences between thermal and non-thermal plasma. Here this is a pot in which we have kept water. This is water, and over that this plasma is discharging directly. What you are seeing here, that the plasma is interacting with the water, but there is no boiling, nothing, and even no sign of any convection that we usually see when we try to boil some water in a pan in our gas oven. Actually the plasma is so cold that you can put your finger over there and nothing is going to happen. So those photographs I will be showing you in the tutorials, that how cold they are. But the interesting fact is that this temperature is well below what temperature I am talking about. I am not talking about the electron temperature, I am talking about the gas temperature. That gas temperature is well below, say, bearable limit, well within, not below, well within the bearable limit of human cells. So let it be around, say, 35 degrees centigrade or 40 degrees centigrade, not more than that. If it is more, then human cell or biological cell cannot sustain that high temperature for prolonged period. So these kind of devices are being used for biomedical applications and then material processing applications quite a lot. The advantage is that it is providing a cold plasma, and the temperature for biomedical application is limited to, say, less than 40 degrees centigrade. But this is not so when you are going for surface processing applications. There the temperature can well be around, say, 100 degrees centigrade, but not more than that. Whereas in your thermal plasma, the temperature of this jet was around 1 electron volt, this gas temperature. So it was more than, say, 10,000 degree Kelvin. And since at such high temperature, this Kelvin and degree centigrade differs a little, so temperature in degree centigrade is also around that, and any material on earth will just get vaporized if you are going to use such kind of device. So they have different application areas, but this one is giving you a cold plasma where your gas temperature or ion temperature is very low, say within 100 degree centigrade or so, but the electron temperature is very high. That may be as high as 2 to 3 electron volt. We are not sensing the temperature in our cells because the gas temperature is so low. The water that you are seeing here is not boiling because the gas temperature is pretty low. The other advantage of this kind of device is that you are seeing here this device, the width or you can say diameter of this device here, it is less than say 20 mm, 2 centimeter. Okay, and it can be even less than that depending on the kind of design that you have made. So it is pretty thin enough. You can hold it between two fingers and you can apply at the zone of your interest. The radicals that it generates are the most important things. The number density of the radicals that has been generated is typically of the order of say 10 to the 19 to 10 to the 20 or maybe around that, bit less, say 10 to the 17 to 10 to the 21. It can vary anywhere depending on the kind of plasma that you have generated or the plasma generation technique, but that is several orders of magnitude low compared to the number density that you usually observe in case of thermal plasma. In thermal plasma, you are generating everything at atmospheric pressure, and you know from the beginning we are calculating what is the number density in this room and all this. So there we have found that number density is 10 to the power 24 per meter cube or around that. Okay. So here you are getting 10 to the power 20. So 4 orders of magnitude difference is there in the number density. So that is why you know the radical density or degree of ionization is very less, but 10 to the power 20 or 10 to the power 19 is also not a very less number as far as the chemical kinetics are concerned. They are sufficiently enough to influence the interaction with your biological cells. Now, what kind of radicals that can generate? That is very important thing. So, suppose it is interacting with water, like the one that you are seeing here. Some of the water molecules, because of its vapor pressure, will be coming out and they will be interacting with the plasma jet. So, what it can produce? It can produce OH radical, and it can break the OH molecule. It can produce hydrogen. It can produce oxygen nascent. Then what it can do? Some of them it can even ionize, depending on the ionization potential. Then you know that OH can undergo reaction and form H2 over there. Then suppose it is now discharging in atmosphere. Then what will happen? It will be interacting with the atmospheric air and it can break that nitrogen molecule and it can produce nascent nitrogen as well. And that nascent nitrogen can react with the oxygen species that has been generated there and it can interact with that to form NO. And NO can eventually form NO2 or NO3 and which can get dissolved in the water that is getting treated at the bottom, and it can stay there as a very stable nitrate or nitrite radicals. Now, you know that these are the agents which can interact with biological cells. You know, this OH radical can damage the cell membrane very effectively. And there are many other applications where this type of plasma jets are being used. We will have an elaborate tutorial session on those applications and what are the different unique potential of these devices that are being explored at present. So, let us come to the plasma source, which is the subject of this class, how they are getting generated. And it is surprising that you are generating in such a small device. The power supply is also tiny, and it is a very portable system. You can put it between your two fingers, and the most attractive part is there. You are producing a cold plasma, but you are not requiring any vacuum. So that is a very very interesting thing, that you are not requiring vacuum, and still you are able to generate a plasma which you can touch it by hand. In the tube lights, you can of course touch it by hand. There you require a vacuum, or the glow discharge plasmas. There also the plasma is cold enough, and there is a highly non-equilibrium plasma. But there, what you require? You require a vacuum, very high vacuum you require over there in glow discharges. And to get that vacuum, you require an elaborate vacuum system which is very bulky. And what you require more is that the time it requires to reach the vacuum level. So you start now, then wait for hours to get the vacuum, then only you can start your device. But this type of device, what I am talking about, the atmospheric pressure plasma jet, they are just plug and play device. You just plug it and immediately you will be able to operate it. It doesn't require vacuum, and it is a very very less power consuming. So that is another very important thing. If you are going to operate a glow discharge plasma, you require so many accessories, and that require or that consumes a lot of energy while you are making the plasma. But here you are using a power less than a watt in most of the cases. So power wise or your energy efficiency, they are very efficient plasma that you are generating here. Now I come to tell you what is the magic behind formation of such unique cold plasma devices. I am showing here a basic diagram. The basic principle is very simple. What you are doing, we are of course using the Maxwell's equation, and you know that the EMF, that Lenz's law, what it says that EMF generated is rate of change of the flux proportional to, and it is of course negative. So if L is the inductance, then L di dt will give you the EMF that is generated. So di dt, that is the change in the current. So how fast your current is changing, so that will give you the EMF that is generated on the other end, and L is the inductance. What we are doing here, we have a this is an example just. So we have a some DC voltage over here. So here incidentally it is 18.5, and there is a switch over here. You see here. So what we are doing, we are switching this device using a square wave pulse. So this current, when the switch is closed, current is passing, right? And then the moment it is off, suddenly the current is off. So current some value to 0, almost instantaneously it is happening, and because of that the DID is very high. So from primary to secondary, so this is a transformer, this is a primary coil, and this is secondary coil. In the secondary coil, the EMF induced is becoming very very high. How much? It is of the order of say 5 to 10 kilovolt. So that is the kind of range the EMF is getting generated over here because of this fast switching. So what you are getting at every falling edge of this square wave pulse, when the switch is opening, you are getting a very high voltage generated in the secondary, and that high voltage is applied across what? You see, the central part is one electrode. We call it live electrode. So that is connected to the secondary. And the other end is the body surrounding this electrode. So both are metallic. The central electrode, usually we use tungsten kind of metal, which can have low work function and which have very good thermal and electrical properties. And the enclosure of that is another metal. It can be anything. You can use copper, you can use SS, that is stainless steel, and that outer body is grounded. So this part is grounded of the secondary transformer, this part is grounded. So you can now understand that you are basically applying a very high voltage between the central electrode and the outer electrode, which is grounded. Now, again our past chain breakdown, which we have read, so that is so useful. Now you can understand that there is a gap which may be broken because of the application of the very high voltage. And where is the gap? So at the top, this is the difference. So this difference is a bit large, but here as you come down near the nozzle section, you see that the gap is very small because of this converging configuration. So the difference, the gap between this central electrode and the ground electrode is very the low, or maybe the lowest at this zone. Wherever it is the smallest gap, because of the high voltage, that breaks. And the gap usually you keep around say 1 millimeter to less than 2 millimeter. So that gap is broken. Now you see here that this pulse is applied, a very high voltage is generated over here, and a breakdown occurred. But that breakdown is only for the period when the high voltage is appearing over here, and that high voltage, once it appears, then the discharge starts and this plasma forms. So what you are seeing here is secondary coil, that is this secondary. Then this voltage is applied between, this is the outer electrode. So this is, you can say that this is some circle, and part of the circle is shown over here. This is grounded one, and this is the central live electrode. So between these two, plasma is formed in this region, and this plasma you can represent using a capacitor and a resistor model. So this plasma, of course, it gives you resistance, some resistance it gives depending on the kind of plasma that you have created, and because there is between two plates some dielectric media kind of thing, so some capacitance it is offering. So basically now you see what you have formed, a secondary coil inductance L, capacitance of the plasma zone, that is C, and a resistance of the plasma that has been formed. So it is now an LCR circuit. This LCR circuit, the moment you put it on, when the pulse is applied, the plasma is formed, then only it is getting on. Otherwise, if there is no plasma, this part is open. Okay. So when the plasma is formed, then it is completing a LCR circuit. So whatever this potential you have applied, whatever EMF is applied across the secondary, now it starts oscillating. The current that is flowing be in this circuit, in this closed circuit, when the plasma is formed, start oscillating. Now I told you that this C and R is determined by the kind of plasma that you have created. Then what kind of plasma you have created? So for that, you need to know what gas you are passing between these electrodes, the central electrode and the ground electrode. So it is your choice whether you want to produce pure argon plasma, or you want to produce pure nitrogen plasma, or you want to make a mix of that, or you want to use some other gas like air or oxygen. Depends on the kind of application that you are interested in and the kind of radicals you want to generate using this plasma for a kind of specific type of treatment or specific type of applications. So that decides the property of the plasma that has been created over here, and it is in your hand. You can control their flow rate, you can control the nature of the gas, anything that you want to do, you can do it through this control, this MFCR mass flow controller. So MFC1 is for this cylinder, and this is for another cylinder. And if you are operating with air, then you require no cylinder. You can just take the atmospheric air and just push into the here. But there you may require a mass flow controller, of course. so that you know what flow rate you are using over there. So now it is very much clear that once a very high voltage is applied across these two electrodes, a plasma is generated, then a circuit is complete, and LCR circuit is formed, which can, as per the physics that you have studied in our classes, graduation classes, so we know that it oscillates, it starts oscillating, and this is exactly what we are seeing over here. The moment the switch is off, that is this zone, actually this is your pulse. So from this 1 to 0 condition, when it is having high voltage, then suddenly switches off. Then at that moment you see that there is a spike in the current that you are seeing over there, and then this spike is inducing a current, and that current is oscillating. And if you look very closely, you will be seeing that the zero line is over here, and the current is oscillating, but it is having a same polarity, that is, it is flowing in the same direction but oscillating. Okay, so that is what is required, because we are using a diode over here, so for some functional purpose, and that is allowing the current to pass through this but in a oscillating mode. Okay, and because after the pulse is applied, the external source is now taken out, there is no supply because it has gone off. So what you are seeing, that this is a damped kind of oscillation that you are seeing. Then a time comes when the polarity reverses, because you are using a oscillator kind of thing, and then what happens, actually the plasma is off because you are not applying any external energy. But what happened, actually the radicals already generated and they are there, so they are now getting collected by the electrodes, and that forms a current in the reverse direction. Now the electrons get collected very fast, then the ions come. So you are seeing that there are two humps which are basically representing the kind of particles are getting collected. So whenever there is a field, that electron will move, suppose right direction, then the current is in the left direction. And but under similar situation, ions will be moving in the left direction because electrons were in the right direction. When ions are moving in the your left direction, then the electron current is also in the same direction. So currents are basically adding. Now the oscillation that forms, that you have seen because of the LCR effect, and these are the kind of current that you are seeing over here, which is measured. And the magnitude that you are seeing over here, it is say 0.1 ampere and less than that 0.05 ampere. That is the kind of current that usually passes through this. Now these are the output voltage what you are getting over here. So these are the range that you are seeing, that it is kV order. So it is around say 12.5 kV kind of thing, and at different excitation frequencies, when you are these pulses, you can control the frequency of these pulses. It may be in say 10 kilohertz, or it may be say 15 or 20. So you can vary that frequency at which you will be applying the external switching. Okay, so if you are doing that, then you see that at 11 kilohertz we are seeing kind of thing, and 14 kilohertz, and you see these two different frequencies we have shown. And everywhere what we are seeing, that you see the current, this oscillating nature, and a positive current, negative current, these features are always present there, and this plasma oscillations. Now one important thing is that you are exciting the plasma, then plasma oscillations start depending on the kind of your plasma that has been created, which is offering certain capacitance and certain resistance. Now plasma is a nonlinear dynamic load. So when your LCR oscillation starts there, the kind of frequency it supports is beyond the excitation frequency. That is what is shown here. So this is the 14 kilohertz excitation frequency, and of course get a 14 kilowatt, this signature in the frequency spectrum. These are the frequencies. But what is interesting is that plasma is showing an oscillation which well beyond this 14 kilowatts. That is the excitation frequency. You are getting a peak at 252 kilowatts, 490 kilowatts, 750 kilowatts. So they are actually some frequencies which is generated in the plasma itself due to its very special nonlinear dynamic nature. Okay. So although you are basically exciting the plasma using some external pulses of certain specific frequency, but at the end the oscillation what you are getting in your plasma kinetics, that is at much higher frequency. So this is very interesting. And this plasma dynamics, whatever is happening that results in wonderful structures within the plasma itself because of the mutual interaction among these fields, the ions and the electrons. So the structures that are usually observed in such kind of devices, they are very peculiar in form. I will show some of them in the at the end. Now here what I am showing here is that the variation of discharge features as a function of frequency. So here what we are showing that the average power dissipated in this as we are changing the frequency, you see that it is increasing and then remaining stable for quite some reason, and then it is again increasing. Okay. So this is the average power dissipated. What is the order? So this order is around say 2 to 4 watt. So that is the kind of power that is dissipated in such devices. As I was telling you that they consume very low amount of power, and the kind of behavior that you are seeing here, the trend may be similar, but actual behavior will depend on the kind of device that you have developed. What you have just seen is a direct discharge device. So there are discharges between two electrodes, two metallic electrodes, where the gap is minimum, there the breakdown is happening, and the gas flowing through that is forming the plasma, and whatever you are seeing here is like that. And the temperature is low. Why? Because the plasma is not continuous, it is in pulsed mode. So whatever plasma is generated, energy is dumped that time, but rest of the time it is dissipating. So the overall temperature of the plasma is not being able to grow. So you are getting a temperature which is well within the bearable limit of even the human cells. Now electron temperature here we have measured spectroscopically, and what you are seeing that the electron temperature is of the order of say 25,000. So that is easily 2 eV, and here you see that it is ranging, it is lowering as you are increasing the excitation frequency. So that is just falling down like this. Okay. Now the plasma that has been generated into that plasma, you see however here the intensity, the moment you change the frequency of the excitation, they are having significant impact on the intensity that is being generated over there. Similarly, you see the temperature, this temperature is around 45 degrees centigrade. So we will operate depending on the kind of application at suitable frequency so that this temperature is below 45 degrees centigrade. So here we can apply, we can use it for even human cells. Then what we need to do, if you reduce the want to reduce the gas temperature, that time you can even bring your specimen to be treated at certain distance from the nozzle exit so that you can get the required temperature. Actually the temperature falls down a very sharp way as you go downstream, that is from the nozzle exit to down, as you move downward, then the temperature falls rapidly. So wherever the suitable temperature is obtained, you can keep your specimen over there. So these are the different structures. You can see the very peculiar structures that are observed in this kind of APPJ devices, atmospheric pressure plasma jets. So, I stop here in this class, and in the next class, I will be taking you to the area of dielectric barrier discharges, where which are some other similar devices in use that can produce cold plasma. Okay, so up to this in this class, we will meet you in the next class. Thank you.